I'm Suman Daj, COO at Axel Technology Forum, and we are back with another deep dive session, this time on a topic that sits right at the edge of theory and the future, a subject that challenges our understanding of reality itself, from classical to quantum computing. Before we begin, let's take a moment to appreciate the pillar that make these conversations like today's possible, the IIT Alumni Center, Bangalore. It is not just any gathering space, it's a vibrant ecosystem built for innovation, collaboration, and impact. What makes IITACb truly unique is its unique and inclusive structure. It hosts dedicated seats for IITs, bringing together a powerful community all under one roof. The center also houses incubation spaces with 180 seats, creating one of the most dynamic early stage innovation environments in the country. And adding to this momentum, this year IIT ACB launched its first Center of Excellence focused on one of the most transformative technologies of our time, artificial intelligence. This COE is also known as the Axel Technology Forum and is already shaping the next wave of frontier tech innovation. Axel, supported by the government of Karnataka and powered by the IIT Alumni Center, is on a mission to build a world-class ecosystem for AI and future technologies. Now, talking about today's session, quantum computing is not just a technological upgrade, it is a paradigm shift. It redefines how we process information, how we understand complexity, and potentially how we solve some of humanity's biggest computational challenges. To guide us through this fascinating domain, we are privileged to have with us two brilliant minds who live and breathe the theoretical computer science, Dinesh and Jaikumar Radhakrishnan. Dinesh will be the moderator for the session today and is an assistant professor in the Department of Computer Science and Engineering at IIT Palakkad. His work lies at the heart of theoretical computer science, where he examines the power and limitations of computational models, both classical and quantum. In essence, he explores the very rules of computation, questioning and expanding the boundaries of what is computationally possible. And Jaikumar Radhakrishnan is one of India's most respected theoretical computer scientists. With research spanning complexity theory, randomness and computation, quantum information, combinatorics, and information theory. After completing his BTech at IIT Kharagpur and PhD from the Rutgers University, he joined TIFR in 1991. In 2024, he moved to the International Center for Theoretical Sciences, Bengaluru, where he is now a distinguished professor. His contributions have shaped fundamental understanding across multiple areas of theoretical CS and quantum computation. And we also have Sushila Venkatramana, Governing Council Member and Joint Secretary at IIT Alumni Center, Bangalore, Director at CGBS Unnati Foundation and Chairperson at Arogya World Trust, who will close the session. So whether you are into academics, an industry professional, a startup founder, or simply someone who loves exploring the future, today's conversation will not only expand your understanding, but also stretch your imagination. Also, during the session, if you have any questions, please make sure you type the same into the Q&A box only. We will not be taking any questions tapped in the chat box. With that, let's begin our deep dive into quantum computing, guided by two extraordinary experts. Over to you, Dinesh.
Welcome everyone. So Jaikumar will be talking today about on the topic of the talk is titled from classical to quantum computation. So over to you, Jaikumar. Please enlighten us with your words.
Okay. Yeah. So can you hear me? Yeah.
Yes.
Yes. Okay. So thank you everybody for coming. My name is Jaikumar Radhakrishnan, and I'm very grateful to Dinesh Krishnamurthy for helping us with this session. As Shuman Das mentioned, I am a theoretical computer scientist. So I will try to tell you what quantum computing means to a theoretical computer scientist, and hopefully I will at least justify your faith in coming here and cover a substantial part of what was advertised in the abstract of the talk. I'm grateful, of course, to the IIT Alumni Center for the invitation to speak at the webinar. Okay. So the plan is this. So we will have two parts. The first part will be about 25 minutes. And I'll try to somehow tell you why how quantum computing fits in relation to classical computing. And we will talk about circuits, randomness, and then I will introduce a quantum experiment well known to physicists, which somehow destabilizes our thinking about randomness. And from there, we will move on to how this spooky experiment can eventually lead to efficiency in computation. Okay. And that efficiency will be demonstrated by a toy example in which what can be done with two quantum probes can actually be done with with two classical probes can be done with just one quantum probe. Yeah. And one can show that one quantum probe cannot do that task. One classical probe cannot do the task, but somehow one quantum probe can do this. Then we will have some time where Dinesh will help me with your questions. And there is a very famous application of quantum information called quantum bomb testing. Depending on the time, I will try to describe this to you. And then the final part after the break will be the quantum factoring algorithm. Again, I mean, it's an elaborate thing. There's a lot to be said and done, but I'll try to give you some idea, and you can ask me questions and that will help. All right, so let me start. So whenever you have a question, please type it into the Q&A part of your screen. But it will help Dinesh and me to answer your questions if you included the slide number. Yeah, so the slide number appears at the bottom right. Yeah, here. Can you see? Yeah. So, and then, you know, what is your question, whether it is a question about something I said, or it is just a general comment which is of one of these kinds. But any other question is perfectly fine. Please type it and Dinesh will decide how to present it to me. Okay, good. So now we really start. Okay, yeah. So, okay, so this is blocking our view. Okay, yeah. So we all have started programming. Everybody knows what a computer does, and everybody has done a little bit of coding in life. So I really don't want to start with the definitions, but just a general remark about when you have a computational problem. Yeah, you have a problem which you think your computer might be able to solve for you. What do we mean by the computer solving the problem for you? Yeah. So what is a solution to a computational problem? Well, a solution to a computational problem is a method for transforming the input to the output using some basic steps. I'm sorry, this is really annoying. Using some basic steps. So what we desire is a method for solving a problem. So for example, in school, we are told how to multiply numbers. So the solution to the computational problem of multiplication is a method. The method that our elementary school teacher teaches us, that is the solution to the problem. Yeah? We are not talking about an instance of a problem where we are asked to multiply 256 by 394. Okay, that's an instance of the problem. What we are interested in is a general purpose method for solving the problem, which in computer science is usually called an algorithm. Okay. Now, I've mentioned basic steps here, but what do we mean by basic steps? Now, what basic steps you are allowed to perform on the data depends on the model of computation, And many of us use programming languages like Python. So then the steps that are allowed in a Python language become the basic steps. And in some of our solutions, we will see we are allowed to use random actions. That is, we can toss coins and based on the outcome of the coins, decide the next action to perform. So algorithms that involve random actions are called randomized algorithms. And when you have randomized algorithms, you are prone to errors. And when we try to analyze algorithms that involve randomness, we have to pay attention not only to efficiency, but also to the probability of error. Okay. So overall, the goal of computer science, or at least complexity theory and algorithms, is to design methods that are efficient. And by efficient, now efficiency can be with respect to many resources. So often we would like our algorithms to run fast. Sometimes we are okay if the algorithm runs a little slower, but it must not use too much memory, or it must not use too much power, or it must not depend on too much randomness. And perhaps in Bangalore, where there are so many industries and software companies, we don't want a genius solution which nobody understands. Okay, so we would like solutions that are easy to describe and modify and debug. All these are somehow resources. They make our task easier or harder. Okay, so we will most of the time today we will think in terms of time, which we will measure in a slightly different way. So let me just describe that. So today our model of computation is going to be circuits. All right. Now what are circuits? Yes, so you all seen circuits. They have these gates, ands, ors, and nots. And they have these inputs here. And these inputs are transformed by gates bit by bit, and they travel along the circuit and eventually produce the output. Yeah, the output comes up here. Now, when you want to perform a computational task is a certain relationship between input and output, and you want to realize that relationship using a circuit. And when we try to think of computation in this fashion, so our basic operations are these, then we would like to know what it means to be efficient. And for today, our idea of efficiency is try to convert the input to the output with the fewest possible gates. Okay, so you've been told that you will be supplied some n-bit input, and there's a particular output that is demanded of you, and you have to give me a method by which the input can be transformed to an output by means of gates. And there may be many methods which compete with each other, and the method that uses the fewest gates will be the most desirable. Okay. Now, it turns out that with ands, ors, and nots, every function can be realized, but every function can also be realized by a somewhat less familiar gate, which is called the Toffoli gate. So it's not terribly crucial for our discussion today what a Toffoli gate is, but if some of you go back after this webinar and look up some books on quantum computing, you will see that Toffoli gate is mentioned prominently. So I would like to quickly tell you what it does. So a Toffoli gate is an object like this. So it has 3 wires. Yeah. So the first 2 wires, which I have called X and Y, yeah, X and Y, they come in and go out as it is. Okay. Sorry, what did I do? Yeah, this is Y. Yeah. They come in and go out as it is, but what they do is they influence the 3rd wire. If both of them are 1, then the 3rd wire flips. That is, if it was carrying 0, it will now become 1. If both if X and Y both are 1 and this one is 0, then the output will become 1. And if this one is 1, the output will become 0. But if either of them is 0, then nothing happens to the third wire. So that's why these bits, the top 2 bits, are called controls, and this is the target. The third bit is the target. Okay. So this is a Toffoli gate, and you can see that if you applied the Toffoli gate once again to the output here, you will get the input back. So you see, unlike and or, which are not invertible gates, Toffoli gates are invertible. A Toffoli gate is its own inverse. And this is an important property because in quantum computing, if you want to embed classical computing as part of quantum computing, then it is important for our gates to be reversible. This is because of physical reasons from physics. And one of the cleanest ways of sort of convincing ourselves that quantum computing encompasses classical computing is to visualize all our computations, all these gates, in terms of Toffoli gates. But this is just for the future. It will not be.
So, Jaikumar, just to clarify, I'm just trying to see how would it be, how is it that Toffoli gate is its own inverse? Is there a example or
Is there a way? Yeah. So
way to see it?
let us look at this formula. So I've described Toffoli gate's operation as x, y, z. So this is x, this is y, and let me write z here. Yeah. So x, y, z becomes x. So the x goes out as it is, the y goes out. So this x is the same x, this y is the same as this y. The only thing that changes is z plus xy. Now, what does this plus mean? This is addition modulo 2. Yeah. So if you applied the Toffoli gate to itself once again, then you would do x, y, z plus xy. And the next
So,
Toffoli
Jaikumar,
gate that
sorry.
you
So,
will
what is xy here? It's multiplication,
x
right?
multiplied by y.
By
Yeah.
yeah.
So or an and. Yeah. When
And
x
yeah,
and y are zeros and 1. So xy means x multi. So if both are 1, then xy is 1. And if even one of them is 0, xy is 0. That's right. Yeah. Thanks. Yeah. So if you do this z plus xy and then again plus xy, if you add xy to itself twice, because we are doing everything modulo 2, yeah, it will get erased and z will be restored on this line. Okay. Yeah. Good. Thanks. Okay. So now you might wonder why this circuit model is realistic after all. Yeah. But if you think about your computer, what is your computer? Computer is some hardware. And in each clock cycle, the current data in your memory is acted upon by this hardware. And then some new configuration results in your memory. And then the hardware again acts on it, the hardware again acts on it, and in the end, you get your answer. Okay. So if you think about the total amount of work your computer has done, it amounts to counting all these gates as many times as the time it took for your algorithm to finish. Okay. So counting the total number of gates in this circuit corresponds to the total amount of work, total amount of power or effort needed in this computation. So I'll let you just accept that counting the number of gates is a very reasonable thing to do. Okay, good. Now randomized computation. Yeah. So in randomized computation, you have these same gates and ors and nots, which we may then now realize using Toffoli gates. But you also have these special gates, which are called dollar gates. And what a dollar gate does is no matter what its input, its output is 0 or 1 with probability half. Okay. So if you give it a 0, the output here will be 0 or 1, both with probability half. Okay. So it's as if the dollar gate tosses a fair coin and the outcome is put out on the output wires. Now, if you
so the
fix, question.
So Jaikumar, the output comes on both of them or only
The output comes at this point, which is transmitted along these lines.
these two lines? Okay.
And it will be the same. If this one is transmitting 0, this one will also transmit 0.
But that happens with probability half.
Yeah, both will be transmitting 0 with probability
Zero
half, and both will be transmitting 1 with probability half.
Probability half.
Okay, good.
Thanks.
Yeah. So yeah, the same here. This is just, I'm tapping the wire, so to say. Okay. But the important thing is that when you have a randomized algorithm like this or a randomized circuit, the output is not fixed. For the same input, depending on how the coins turned, the output can be 0 or 1. But what we want is that the correct answer should come with very high probability. Yeah. So for whichever problem you're solving, we would like this randomized method to give the correct answer with, say, probability at least 3/4. This 3/4 is not a serious number. I'm just writing it because I want some number better than half. Okay, good. Now, this 3/4 can be proved to 99% or 99.99% by just simply repeating the algorithm many times and taking the majority of what the outcomes were. Okay. So now, so far, we have an idea of what a classical deterministic computation is. A classical deterministic computation is a computation performed by ands, ors, and nots. A classical randomized computation is a computation performed by ands, ors, and dollars. Yeah. Now, randomization is a very important thing in computing. The most important, perhaps, is that cryptography depends on randomization to a large extent. There are many problems for which the most efficient solutions we know are randomized. The amount of error that randomized algorithms usually introduce are rather insignificant. They never cause serious problems. The probability of a device failing is usually much higher than the probability that the algorithm does something wrong by design. Okay, good. All right. So
Jaikumar, I just want to clarify. So here you have drawn a wire as input to this dollar gate.
yes,
So the output of the dollar.
the output of the dollar gate ignores the input. Even I have put the wire coming into the dollar gate because I will later on do something else similar to a dollar gate where the wire will be important. Okay. But yeah, so it is as if you have a particular location in your memory, you toss the coin and you put the outcome of the coin toss into that memory. So whether it was 0 or 1, it gets erased and the outcome of the dollar gate goes and sits there. Okay, good. So finally, yeah. So now, so just whatever I have said was probably familiar to you. I've just said it in a strange way. But what is going to happen today, or what drives the discussion today, is something like this experiment. And I would really like to spend the next maybe, yeah, I don't know how much time I have, but maybe 10 minutes on this experiment. So here is what the physicists observed. Yeah, so this is what the physicists observed. So they have this device. This is, I should have mentioned. Yeah, so what is this is the Max Zehnder experiment. So you have a beam splitter here. So this is an experiment done with photons. Yeah, so you have a beam splitter here. And if a photon approaches a beam splitter, maybe I should just change my color. So if when it approaches the beam splitter, it can go up or in this direction with equal probability. Okay, so if you send a photon through this beam splitter and put a screen here, you observe that the photon comes out, either it hits this part of the screen or this part of the screen roughly half the time. Okay, good. And then this is just a mirror. It sends the photon this way, and then again, this beam splitter, this is a splitter bit, actually it combines the two photons and then it sends it off either here or here, and one of these two detectors detects them. All right. So there is one detector here, one detector here. Yeah. And the photon comes this way. Yeah. Good. Now here is the strange thing. Suppose I were to block this. Yeah. I block this part and send the photon this way. if I send the photon, a single photon, yeah, if I send a single photon this way along this, what happens is that you see it here or here with equal probability. Yeah. Now, but if I remove this and then send the photon, it always comes up. Yeah. So when the top beam is blocked, either detector may receive the photon. When the bottom beam is blocked, then the photon can show up here or here with equal probability. But when both beams are allowed, then the photon always shows up, let's say here. Yeah. Now, how do we explain this? Sorry, how do we model this in probability? We can always imagine that photons are like balls, and maybe there was a little pin here, and the ball bounced off this pin and went this way or this way. Okay. And then maybe it got reflected, and here some combination happened, and then the photon showed up here or here. But if we think as we think with usual probability, then if it is the case that when the photon goes this way, it reaches both these, it is capable of reaching both these. When the photon is sent this way, it is again capable of going both ways. But if I leave both these channels open, then somehow photon never reaches here. It's a single photon. Yeah. How did the photon traveling this way know that this channel was even open? Yeah. And these experiments have been done, and these mirrors have been kept far away. It is not likely for this photon to have somehow signaled to a part of the photon here about what is happening. And whenever we place a screen, it's only one photon. So one could perhaps give a plausible explanation that what we think of as one photon is actually two photons. The moment the photon comes here, the photon splits into two parts. And then when it comes here, it again combines. But all that has been ruled out. When we place a screen here, we always see it either here or here. We never see half the intensity at two places. We either see full intensity in one place or full intensity in another place. Okay. So this is a very puzzling thing, and this is at the heart of quantum mechanics. Okay. So I'm going to now write some symbols on the screen, yeah, and try to make sense of this, or try to tell you how physicists make sense of this. Okay. What they tell us is actually happening in this. They say there is nothing called a photon. Okay. It is just a tendency. Yeah. So let me try to explain. So when a photon is sent this way, let us say that it is a horizontally traveling photon. Yeah. So a photon traveling this way, let me call it 0. Yeah. So a photon is in a state 0. Please don't be alarmed by this decoration that I have put around 0. This is just because that's what they do in quantum. Okay. So in the beginning, the photon is in state 0. Then it splits, or it encounters the beam splitter. Okay. Now, in classical probability, if we threw a ball at a peg and the ball, we imagine, would then go either get deflected this way or that way, we would say, oh, classical probability would say it with probability half, it goes up, and with probability half, it goes horizontally. This is how we would think of a photon or a ball which bounces off a peg and might either go up or go right. Okay. Then what happens? Well, this ball, which was going upward.
Jaikumar, I'm slightly confused between this peg and photon analogy. So with respect to, what goes on when it is a ball, and what goes on when it's a photon?
Okay. So what is a beam splitter in quantum is peg for me in like my pen. If I threw a ball at this pen, it might deflect this way or this way. Okay.
Correct.
But if a priori, I had to imagine what would be the state of the ball after the peg. I would say that, oh, it will be here with probability half and it will be here with probability half. So it will be either 0 with probability half or 1 with probability half. Okay, that is how I would have imagined the ball to behave. And then I would have said when this 0 enters this device, which I can again call a peg, then it would reflect this way or this way. So a ball traveling this way would have probability half times half, that is 1/4. And the ball traveling this way and continuing this way would again be 1/4. But overall, if the ball were to, if I have to reckon the total probability, then I would say 1/4 this way, and the probability of going this way is also 1/4, and the total will become half. And similarly, I'll be able to explain that it comes out here with probability half. And there is no escaping this conclusion. Yeah. But in quantum, the probability of going on top is 0. And how is that happening? When if I block only one of them, it reaches both of them with probability half or gets trapped here. That's a different matter. And when a photon takes this route, again it goes to these two detectors with probability half. So the way the physicists sort of come to terms with this is say that when the photon is at this point, its state is something called a superposition. Okay, a new word. As if the photon hasn't made up its mind yet. It is in a superposition of 0 and 1, and they write it like this. All right. Okay, so very good. I mean, as far as somebody who has looked at probability, nothing very strange has happened. You've just defined, instead of half, you're writing 1 over square root 2. And there is a 0 and there is a 1. You're stuck in a plus in the middle. But nothing new has happened. But the strange thing is, okay, so how do they manage to explain the outcome of this experiment? They then say that when this 0, which means the photon traveling this way, encounters this beam splitter, this 0 again splits into yes. And this is where it gets a little spooky. This one, so if the photon was presumably traveling this way, it again splits into 0 and 1. But this time, so this 1 over square root 2, I have just copied from here. Okay. And then.
So Jaikumar, just to clarify once again, so how did we get that first term there?
I'll tell you one second.
Yeah, sorry. Yeah.
So good. Yeah, so the first term here.
Yeah. First term there. How did that 0? Yeah.
Yeah, so this, whenever a 0 encounters a beam splitter, it turns into an equal superposition of 0 and 1. And whenever a 1 encounters a beam splitter, it again turns into a equal superposition of 0 and 1, except that there is a minus sign. Now, when we do classical probability, there is nothing called negative probability. Okay. In quantum mechanics, you have negative amplitudes. These objects which we write in front of zeros and ones are called amplitudes. In classical probability, we would have called them probabilities. And here you have amplitudes. Okay. And last time you saw that when it was half, and then we multiplied it again by half, and it became 1/4. The same thing is happening here. 1 over square root 2 is getting multiplied by another 1 over square root 2, and it will become half. But when you are in such a state, and you want to know what is if I were to now observe or perform a detection, what's the probability of seeing a 0? It is the square of the amplitude. Okay, so that is the difference between classical probability. In quantum, you write amplitudes, which are the square roots of the actual probabilities that will arise. Okay. So the way the physicists deal with this experiment is, imagine that the state of a photon is actually a superposition, where amplitudes play a role and amplitudes can be negative. Then when a device encounters a photon, it just transforms it into a 0 and a 1. That means either a vertically traveling photon or a horizontally traveling photon, each with its own amplitude. And you do this calculation, and what do you see? Somehow the term 1 cancels off, and all the probability accumulates only on the state 0. Yeah. Now, if you had blocked off one of these, the photon would have only traveled this way. That means only this part of the calculation would have remained. And then you would have seen 0 or 1 with equal probability. And if you had blocked off this, you would have again seen 0 and 1 with equal probability. But when you leave both channels open, somehow some cancellation happens, and physicists call this destructive interference. This destructive interference of probabilities or amplitudes is a uniquely quantum thing. It's a nuisance for us today, or in this experiment, because it kind of slightly unsettles us. But this is where quantum computing derives its power. Okay, so let me just tell you one thing, and then I will stop and we will have a small discussion about the nature of these quantum things. Okay, so if you think about a classical bit, where does it reside? Well, a classical random bit is a probability distribution involving 0 and 1. So it can be, say, 20% 0, 80% 1, or 90% 0, 1%, 10% 1, or 50% 0, 50% 1. So the two numbers determining the probabilities of the outcomes, yeah, let's call them P0 and P1. P0 plus P1 always adds up to 1, because either it is 0 or it is 1. And so a random bit, its state resides on this line. On the other hand, a qubit, yeah, which can either be 0 or 1, yeah, a state of a system, yeah, can be in one of the states, but that state consists of two numbers whose squares add up to 1. And why are their squares adding up to 1? Because the squares correspond to probabilities. But you are allowing negative numbers. Okay. So maybe, yeah, we will just pause here. It's been about 30 minutes, 35 minutes. Yeah. So this is a good time if there are any questions or any clarifications already. If not, we can move on. Yeah.
Yeah, so there is just maybe one or two quick questions. So one of the question that it's natural to ask is, like, for instance,
Yeah.
so for a randomized algorithm,
Yes.
okay. So what you mentioned, that you can actually, if a randomized algorithm is, or a procedure, if it's making errors, you can actually repeat the algorithm and reduce the errors to such an extent that you won't even, the error is smaller than the error that the underlying hardware is going to make. So
Yes.
so in that sense, is that really something that is as good as a deterministic procedure?
For all practical purposes, it is as good as a deterministic procedure.
Deterministic procedure. Okay.
For
So
practical purposes. Intellectually, of course, it leaves us a little uneasy that our algorithm is not foolproof. Okay. But
okay.
I think for any practitioner of algorithms, if you knew that algorithm, its probability of error is only 0.9999, they will say, okay, I will just run it 10 times and take the majority of the answers, and practically there is no chance of an error. Yeah. So that was one question. Yeah, thanks.
Yeah. So I think maybe so there are a couple of more questions.
Yeah, please.
I think some of them will get answered as we move ahead. So maybe we can pause for some time and then.
Yeah. Okay. So maybe I'll move on now, or
Yeah. Sure. Yeah.
okay. So those of you who asked questions, we will come back to you. Yeah,
Yeah.
if you still need an answer. So whatever I said in pictures here, uh, yeah, in pictures here, I have tried to say this. So first of all, yeah. So I think I would really urge you to keep these things in mind. Yeah, the main difference between classical and quantum is that in classical, the state lives in the positive quadrant. In a quantum, the state sort of inhabits the entire plane. Okay. Actually, I'll say a little more. So whatever I said earlier, if you have a random bit, a single bit, then its state is described by two probabilities, the probability of 0 and probability of 1, that add up to 1. If you had n qubits, yeah, suppose your memory consists of, sorry, n random bits, well, they could be in the state 00000, 0000001, or 10000, or 1111. There are 2 to the power n possibilities, and each of them could have some probability. So when we try to visualize classical probability, classical randomized computation as a state, it corresponds to big vectors, huge vectors, which have 2 to the n components. These components are never stored in our computer. Okay, these are things that help us visualize how the computation moves, yeah, in the space of probabilities. Okay, and when any gate is applied to a randomized computation, it just moves probabilities from one state to another, and the probability keeps moving, and our goal is to finally accumulate the probability on a desirable state. Okay, this particular aspect, that we are trying to somehow arrange things so that the probability goes and concentrates on desirable states, is something that is common to classical as well as quantum. Okay, in quantum, you again have a state which is described by two numbers, alpha and beta. Yeah, so alpha and beta, alpha is this way, beta is this way. Yeah, and the sum of the squares add up to 1. In when we need to do more complicated things with physics, these alphas and betas can also be can all be even complex numbers. That's why I've put some absolute values around them. But in quantum computing, we never need complex numbers. Okay, we can get away with just classical, real numbers, but it's convenient to have them sometimes while designing algorithms. Okay, so I've told you what a state of a qubit is. Yeah, and if you have multiple qubits, the same thing, it will become a long vector. It will have 2 to the n components, but these 2 to the n components will be positive or negative or complex. But the sum of the squares of the absolute values must add up to 1. It will be a unit vector. Okay, yeah. And then
So Jaikumar,
operations. Yeah.
You said that we don't need complex numbers, but can we live with just positive numbers?
No,
Is it
positive numbers will not do. We will soon see an example. In fact, with positive numbers, we could not have explained this experiment,
right?
because it was important for us to cancel off this one against this one. Okay, and that is why when quantum mechanics came about, yeah, I mean, a lot of statistical mechanics and statistical physics had gone on for more than a century. Okay, and a reasonably good idea of probability and probabilistic behavior of physical systems was understood. But this still sort of foxed us, because no classical method where probabilities are only positive succeeds in explaining this experiment. And based on their experiment with, wave nature of signals, I mean, already light was known to be a wave, and using that intuition and in a very creative way, physicists came up with quantum mechanics, which now is a very successful and wonderful theory. Okay, yeah. All right, so let's move on. So that little beam splitter, okay, when computer scientists start thinking about it, they think of a beam splitter also as a gate. Okay, what does a beam splitter do? When you feed it a 0, it sends the photon one way or the other. That means it sends the photon in the, it puts the photon in the state 0 or in the state 1 with equal amplitude, and that equal amplitude is 1 over square root 2, and the amplitude is 1 over square root 2 because its square has to be half. Okay, and if you feed 1 to the this gate has a name Hadamard gate, but Hadamard was a very famous mathematician, and he there is a matrix named after him called the Hadamard matrix, and physicists, or at least computer scientists, generously have decided to name this gate after Hadamard. I don't think Hadamard ever built this gate or thought about this gate himself. Okay, yeah. So now there is this 1, and when you feed a 1 to a Hadamard gate, it also is a uniform equal superposition of 0 and 1, but it is 0 minus 1 by root 2. So let me just explain in this picture. When you feed a 0 to a Hadamard gate, the state that results is this state. 0 and 1 with equal probability, 45 degrees, making an angle of 45 degrees with the x-axis and the y-axis. But if you feed a 1 to a Hadamard gate, it comes out in this direction, making a 45 degrees with x-axis and y-axis, but the 45 degrees is with the negative y-axis. Okay. If you were to observe a photon which is in this state, the state that I currently have on the screen, it will still be 0 or 1 with probability half. Okay. So at this point, one wonders, why are we even introducing negative numbers? Because if in the end for probability, we are going to square it, and a negative number square is always, the sign is not going to matter. The important thing is that when physics plays its games inside, yeah, it does it with the negative numbers in place. What it shows us is the result in terms of probability. Okay, so that is the way we think about it. It looks like there are inaccessible things that physics uses to determine its evolution, but there is only some things that are accessible to us, which we obtain upon observation. And those things lead to probabilities, which thankfully are always non-negative. Okay. So this is what is a hard.
So Jaikumar, just to go back, you were talking about an n qubit, right?
Yes.
So the one that you have shown there, the state of a qubit, is that what qubit is it? Is it 1 qubit? Or
this is a single qubit.
This is a single qubit. Okay.
This is a single random bit. A single random bit can be in the state 1/3, 2/3,
right,
or it can be in the state half, half. Now the first one means it's a biased coin, which takes the value 0 with probability 1/3 and 1 with the probability 2/3. Yeah. The second one, which I wrote half and half, means it's an unbiased coin. Yeah. Similarly, this state is, you can say, an unbiased state. It will take 0 or 1 upon observation with probability half, whereas this one, which is slightly biased towards 1, then 0. Yeah. But
so
it's a state of a single qubit. Even though we are working in 2 dimensions, it is state of a single qubit.
Single qubit.
We have n qubits. We work in a space of dimension 2 to the power n.
Power n. Yeah. Right.
So this is a Hadamard gate. Good. So, and it behaves like
Jaikumar,
this.
sorry to interrupt once again. So could one relate this Hadamard gate to the experiment that we saw before, that
Yes. So
beam
it looks
splitter?
like exactly this. The Max Zender experiment. So it is as if 0 was sent, and what this beam splitter did was applied the Hadamard gate to it. As a result, it became this. But here, when 1 is sent into this beam splitter or beam combiner, same thing, these are usually crystals, yeah, calcite crystals. So when you send a 1 into a beam splitter, it turns a 1 into this state. That means the state 1 is transformed to this state. So it's a gate which takes a photon in this state, and it produces the photon in this state. On the other hand, if you gave it a photon in this state, it will produce a photon which is 45 degrees inclined this way. Okay, yeah. Good. So a Hadamard gate is a quantum version of a dollar gate. Yeah, a dollar gate also, when you fed it a 0, it would come out half and half. Yeah, and Hadamard gate also, whether you feed it 0 or 1, the output probability is half and half, but it seems to remember whether you fed it a 0 or a 1. Because a 0 is sent out as a 0 plus 1, a 1 is sent out as a 0 minus 1. We mortals, measuring it right then, will not be able to tell the difference because we see only probabilities. But nature keeps it, and the fact that nature keeps it allows us to explain the outcome of this experiment. Okay, yeah. Now all this is a theory. Nobody has met and talked to nature, but this is how we, build a theory, do more experiments, and in the end, we see whether it works out or not. Okay. Now there is another classical gate, a sort of a little brother of the Toffoli gate, which is called the C-NOT gate, C for controlled NOT gate, which you can imagine what it does. If you feed, there are 2 wires, and if the first wire is 1, the second one gets flipped. Yeah. So if the first wire is 1, the second one gets flipped. If the first wire is carrying a 0, nothing happens to the second wire. So let's just do one little exercise. So suppose I were to send this state here. Now, it's probably not clear to you what this state means. This state means I should open the brackets. It is 1 over square root 2, 0, 0, plus 1 over square root 2, sorry, 1, 0. I've just opened the brackets here. Yeah. Okay. Now, if 0, 0 is sent into this gate, well, since the first bit is 0, it is going to do nothing to the second bit, and it will come out as 0, 0. But if 1, 0 is fed into this gate, this 1 will then, it's a control bit. So it will act on this and change this to a 1. So the result will be this. Okay. So I have some more exercises for you, but let me, I'm running a little late, but later on I assume the slides will be available to you. You should try out what the control NOT gate does to this. I have written its operations in terms of a matrix, which is not important to us today. Okay, let's move on. Yeah. So finally, all right, so I've told you some physics, and somehow on learning this physics, a computer scientist doesn't want to, talk in the language of physics. He says, okay, beam splitter for you, Hadamard gate for me. Okay, and everything seems to work out. But then a computer scientist in the end is a computer scientist, and they wants to do computation and asks, okay, if physicists really believe this is how things work in nature, can I use this spookiness to do something that classical computation cannot? Okay. So in the next 5 minutes or so, I would like to show you something that can be done with just one probe into memory by a quantum algorithm, but which requires 2 probes to do by the best classical algorithm. So let me explain what the problem is, and then we will see its solution. So the problem is the following. I have a memory chip. Yes, this is again a toy problem. Please don't take it very seriously, but it in principle demonstrates why quantum does something extraordinary. So here's a memory chip, and that is the same M, and it has 2 wires, X and Y. Okay. What this memory chip has is it stores 2 bits, A0 and A1. They can be in one of 4 configurations, 0, 0, 0, 1, 1, 0, or 1, 1. Yeah, we don't know what they are, but we want to access them. And the memory chip allows us to access the data inside using this operation. So you can tell us which bit you want, whether you want A0 or A1. So if you put x equals 0, then you will get A0. And if you say x equals 1, A1 will appear. But where does it appear? Okay. So whatever you send in as address, that is 0 or 1, that address will be faithfully returned to you. Okay. In addition, the data that you seek will be returned on the second wire. How? Whatever you feed here, I will add the corresponding bit to it modulo 2. Okay. Yeah. Now you can again, as we did in the case of Toffoli, you can check that this is actually a reversible operation. If you applied the same memory chip to itself, you will be restored to x and y. Okay. Because you are doing this modulo 2 addition twice, and modulo 2 addition done twice is going to cancel things off. So in other words, if you send 0y into this chip, what comes out is 0 and y, but A0 is added. And if you send 1 in the first wire, A1 is added to the second wire. And this plus you should think of as modulo 2 addition. 1 plus 1 is 0. 0 plus 1 is 1. Okay. Yeah. And you're given this chip and you want to know, in the memory that is inside the chip, is it the case that the two bits are the same or are they different? Yeah. If they are same, then their modulo 2 sum will be 0. And if they are different, their modulo 2 sum will be 1. Okay. So this is what we want to do. We have this chip and we want to know whether A0 is equal to A1. Okay. How would we do it classically? Let us just decide. So we would probably first feed 0 into this chip so that we get hold of A0. And then we will feed 1 into this chip so that we get A1. Okay. Now this y I have set to 0 here so that 0 plus A0 becomes A0 itself. 0 plus A1 becomes A1 itself. And now that I have A0.
Sorry, Jaikumar, I missed that last part. Why are you setting that last bit to the second bit to 0?
0, because the output is whatever is the second bit plus the data that I desire. I don't want this second bit to kind of, annoy me. So I have just forced it to 0. Okay.
Sure. Thanks.
Yeah. So I have put a 0 here. And in this case also I have put a 0 here. Here I get A0. 0 plus A0, which is A0. 0 plus A1, which is A1. And at this point, I do a control NOT on this. So if A0 and A1 both are 1, this A0 will flip this A1 and I will get a 0 here. If both of them are 0, again I will get 0 here. But if one of them is 0 and the other is 1, I will get a 1 here. Basically, by looking at this bit in the end, I will know whether A0 is the same as A1 or not. Once again, this control NOT behaves like this, that the final outcome that arrives here is 0 if both these bits are 0. And if either of these bits is 1, if one is 1 and the other is 0, then I get a 1 here. Yeah, because 0 plus 1 will be 1. And 1 plus 1 is 0 and 0 plus 0 is also 0. Yeah. Okay, so this is how we would do this problem in a classical lab. Yeah, we will build a circuit and we will have 2 copies of M. In other words, we have made 2 probes into the memory and extracted the data and combined them to get our answer. Nothing extraordinary about this. The strange thing is that a quantum circuit will manage to do this in just 1 probe. Okay. And so the memory chip is used only once. Okay. And you use Hadamard gates. Yeah. So, and somehow the outcome is the following. If A0 is equal to A1, this A0 and A1, which are here, if they are equal, this output that you measure here will always be 0. And if A0 is not equal to A1, the output here will always be 1. Okay. So I'll I mean, a complete analysis of how this comes about will take us some time, but I'll give you some idea. Yeah. So, but the thing to note is there is absolutely no way, even with randomized computation, to perform this task classically without making a 50% error. And any problem, I mean, this problem can always be solved with 50% error because you don't even look at the input, you just toss a coin. Actually, a dollar gate is a perfectly good answer to this problem, but it is wrong half the time. Okay. And it turns out that even if you look at the memory, but look at it only once, then you can process your data as much as you want, do any number of randomized dollar gates, you will still be making a probability of at least 50% on some input. And this quantum algorithm, remarkably, uses this memory only once, memory chip only once, and gets the answer with certainty. It tells you whether A0 is equal to A1 or A0 is not equal to A1. And in the end, the point is this, that when this particular thing is applied, I would invite you to kind of do the manipulation and the algebra yourself. The state of this register here, in one case, in this case, it becomes and the state of this register in the other case becomes and we know that a Hadamard gate, I didn't tell you. So a Hadamard gate is its own inverse. So if 0 is taken to 0 plus 1 by root 2, a 0 plus 1 by root 2 will be taken to 0. And a 0 minus 1 by root 2 will be taken to 1. Okay. So Hadamard gate is its own inverse. I had written it here but didn't emphasize. Yeah. So that is what works here. The state is this or this. On our circle, it is either this state or this state which have a 90 degrees between them. These are orthogonal states. And it's a general principle of quantum computing or quantum mechanics that when you have orthogonal states, there is some measurement which can completely tell them apart. Okay. And that is what is happening. In this case, the measurement involves first applying a Hadamard gate and then looking at that register. Yeah. The wires are called registers in quantum computing, not important. Yeah. All right. So actually, my original plan of the talk was to reach here at the 25-minute mark and then pause for questions. But maybe we can still do that. We can at least pause for questions and then move on. Yeah. So if there are questions which are
Jay,
There
I
are
think
questions.
we can go on
I can-
because I think the second part of the talk is just as interesting and important,
Okay,
and
good.
we'll take on more questions at the end.
Okay, so then let me skip this. So there is, I think you should all look this up. There's something called a quantum bomb tester. Okay, and it manages to test a bomb without exploding it. Okay, and if we were to it's it's very spooky, but nothing that we know about quantum mechanics says that this will not work. Okay, so this is an area of non-destructive testing, which is very important for checking things which are very small, but yeah, for another time. Yeah, and not today. All right, yeah, good. So yeah, this is the punchline. So the factoring problem. Uh, so sorry, please take a deep breath. Yeah, I'm back to high school now. Okay, so what's the factoring problem? You're given a big number. Yeah, your teacher, is very busy and writes this number on the board and asks you to factorize it. Okay, so this is the problem. And we want a method which, when given this such a number, which I call capital N, and it has n bits. Here, of course, I've written them in digits, but you can imagine in a computer, it will be a string of bits. And given such a number, you have to factorize it. Give me two factors. Yeah, write it as a product of two factors. Okay. Or say that this number is a prime number. Okay. So this is the task. And is there a method to do this? For example, if 37 was given, your correct answer is n is prime. Okay. And if 91 is given, you have to say that 7 times 3 or 7 times 13 or 13 times 7. Both answers are acceptable. Okay. Yeah. So is there a method to factorize a number? Now, of course, this is a fundamental question. I mean, you can imagine that this has been a question for more than 2000 years. The moment people invented division, they would have liked to know whether a big number can be broken up into smaller numbers. And it's a very well-studied problem in computational number theory. And unfortunately, we don't have an efficient algorithm for this problem. Okay. And in fact, it's good that we don't have a solution for this problem, because if somebody could solve this problem, then they could take all your money. Because many of the cryptographic systems that are deployed when computers communicate with each other, or digital signatures, are based on the fact that people cannot factor fast. Yeah. And the best algorithms that we know for an n-bit number, they take time, which grows as exponential in n. Yeah, exponential in n to the power 1/3. But imagine that, you have, so a big number of over 1000 bits, and there are even constants here, and you take 1/3, and it will just, if the numbers are very big, it will take a lot of time. Yeah.
So Jaikumar, this n is the input number, is it? Sorry.
No, n is the number of bits in the input.
Okay.
Capital N is the number itself, and n is the number of bits in the number. So, yeah. So any algorithm that we know today, is too inefficient to break the cryptography of today. But before, it turns out that there are quantum algorithms which can solve the factoring problem. And that is Shor's algorithm. And in the remaining time, I want to give you some idea of how it works. All right. But there is a sort of a little cousin of the factoring problem called the primality testing problem. That is, given a number, I don't want you to factor. Just tell me whether it's prime or not. Okay? Just tell me whether it's prime or not. And this might come as a surprise to those who have not seen this before, that we can tell whether a number is a prime number or not very quickly. But when we see that the number is not prime, we have evidence that it's not prime. We have irrefutable evidence that it is not prime, but still we can't find its factors fast. That is the state of technology today. Okay. But the fact that primality testing can be done efficiently is one of the gems of theoretical computer science. And it all started in the 70s. So there are algorithms due to Soloway and Strassen. Yeah. So unfortunately, they are not in the right picture. So this is Soloway and this is Strassen. And this is Miller and this is Rabin. Okay. Yeah. So there are two popular algorithms for primality testing. Randomized primality testing, they run very fast, and they are due to Soloway and Strassen and Miller-Rabin. But I mean, the great news about 23 years ago, was a deterministic algorithm. This was a randomized algorithm. So our colleagues, two of them were undergraduate students at IIT Kanpur, they discovered a deterministic algorithm for primality testing, which runs efficiently. Okay, it runs efficiently in theory. For practical purposes, we still use the randomized algorithm, which partly answers the question that Dinesh mentioned. For randomized algorithms, for primality testing, we continue to use the error-prone randomized algorithms and leave this and celebrate this only as a theoretical achievement. Okay, it's one of the greatest achievements from scientists in our country. Yeah. Okay. So, yeah, in the remaining time, I would like to tell you about the central features of the quantum factoring algorithm. What is there on this slide is essentially classical. Okay, and all this was known 50 years ago. Yeah. So we are, again, let's get back. What's our problem? We are given a number, capital N, which has little n bits, and we are even told that it is not prime because we ran the other algorithm and it told us that it is not prime. We are just asked to find its factors. Yeah, find one factor. Yeah. So here is the algorithm. Pick a number a, yeah, and try to divide n by a. Or rather, you compute the GCD of a and n, the greatest common divisor. Yeah, I don't know what sometimes it's called HCF, but yeah. So greatest common divisor, biggest number which divides both a and n. If they don't have a common factor, then we move on. Yeah, but if we find a common factor between a and n, then we are done because that common factor divides n and it is strictly less than n and it's not 1. Okay, so if we picked a random number and the GCD comes out to be a number other than other than 1, then we are done. Okay, so then we have our factors. Question: can we efficiently compute the GCD? Yeah. Now it turns out that one of the algorithms that we were taught in elementary school, I don't know how you were taught. You used to write a number here and do this and do this and do this and do this. And in the end, the GCD showed up here. Okay. I don't know if this is what is taught in schools, but that algorithm is actually an efficient algorithm. And that is called Euclid's algorithm. I have a picture of Euclid, of course. Yeah. Later. Okay. Now, all right. So, but suppose the GCD comes out to be 1. What will you do? Okay. So here is the second step. And this was also an old step. You try to find the smallest r so that a to the power r is 1 modulo n. Okay. So you take your number a, multiply it with itself until it becomes 1. Okay. Now there is a simple theorem in number theory that saying that this will happen. It will come to 1 at some point. And you have to find this r. And if you find this r and this r happens to be even, consider a to the power, sorry, when I say it comes back to 1, this might have puzzled you. We do all computations modulo n. Yeah. Of course, if you have a big number and you keep multiplying it with itself, it's only going to become larger and larger. But if you keep reducing it modulo n, eventually it will become 1. Okay. And we want to know the first time when it becomes 1. And suppose it became 1 in, let's say, 118th step. Yeah. Then raise a to the power 59, half of 118. Okay. And if it is a number other than +1 or -1 modulo n, -1 means n minus 1. Yeah. Either it is +1, if it is anything other than +1 and -1, then we have found a factor. Okay. And all this was known 50 years ago. Yeah. And how do we find this factor? This is also easy and within our reach. Oh, by the way, this is Euclid. Yeah. So
sorry, Jaikumar, just one case missed out. What if r is odd?
R is odd. Yeah. So I have written if not ... and I will come to that ... Okay. So if R is even, we are done. If R is odd, well, you try again. All right. Yeah. Pick a new number. And there is an analysis which says that 50% of the time you will be in this even case. So if you run this algorithm 10 times, if you do this 10 times, with high probability, you would have landed in this even case and you would have found your factor. And you would have found your factor because, see, a to the power r over 2, a to the power r is 1. That means a to the power r over 2, if I square it, it's going to be 1. So let me call a to the power r over 2 as b. So I know that b squared is 1. Another way of writing it as is b squared minus 1 is 0 modulo n. That means b plus 1 times b minus 1 is 0 modulo n. So what do we know? Here is a number b, which is neither plus 1 nor minus 1. If it was, why do we know that it's not plus 1? Because r is the smallest. If a to the power r over 2 was plus 1, then r over 2 would have been the number which, which when used as an exponent makes the result 1. So we know that b is neither plus 1 nor minus 1, which means neither of these two factors is divisible by n, but their product is divisible by n. So just imagine, here are two numbers. Neither of them is divisible by n, but their product is divisible by n. That means one of them has some of its factors and the other one has some others of its factors. Now we want to suck out these factors. So you just compute the GCD. I mean, among the beautiful algorithms in number theory is Euclid's algorithm. And it's an ancient algorithm. It's taught to us in school and it still works. Okay. And it works in very modern settings. Okay. So remarkable. Yeah. So anyway, the problem, the elephant in the room, which I avoided looking at, is how do you find the smallest r? This r could be an exponential number. Yeah, it could be an n-bit number. You probably need to raise a to a big number before it becomes 1. And nobody knows how to do this classically. And the miracle that Peter Shor showed us was that you can do this classically. Okay. And let me just tell you how it does, and then I'll stop. Okay. Sushila, should I stop or can I?
No, please go ahead and complete. This is very interesting. Please go ahead.
Yeah. So here is how it works. So yeah, let's read this together. So it says, prepare a uniform superposition over values 1 to n in an n qubit register X. So here is a wire in which we put all these numbers 1 to n, each with amplitude square root n. Let's say 1, maybe, yeah. Each of these numbers I put with equal amplitude. Yeah, it's as if I picked a random number, but this is quantum picking in a quantum sense, any of these numbers. And using this number, yes, let's continue reading. Yeah. So we have another register here, which is y. So this was x, and this is y. Using the information here in this register, you compute a to the power x. What is a? A was the number that we picked in the first step classically. Yeah, this a. So you feed that a into some device and use this x that is moving here and somehow compute a to the power x. All this can be done. Yeah. And how do you compute a to the power x? Because you're trying to multiply a with itself x times. And x can be a huge number. How do you multiply a with itself n times? Amazingly, this can be done efficiently. And it was first discovered. I mean, the only historical records of this algorithm are from an ancient mathematician called Pingala, who lived in India in the 2nd century BC. And this is called modular exponentiation by repeated squaring. Yeah, by repeated squaring, Pingala told us how to compute a big power of a number. And in modern settings, we do it modulo n. Okay, good. So once you have done this, now the trick is you measure this bit. Measure these registers, you measure them. Yeah. So you get some outcome. And the interesting thing is, this outcome is not important. Yeah. What happens to the state of this register? This register has been consulted while computing a to the power x. A to the power x was traveling in this, and these two registers have become entangled. And the moment you measure this register collapses. It collapses into a state, yeah, which is periodic. That means it has values 0, 0, 0, 0, all zeros, then 0, then a value, 0, then a value, 0, then a value. And this, the periodicity of this is actually the number R that we seek. Okay. Now, electrical engineers tell you that when you have periodicity and you want to know the frequency, yeah, you have sound, signals, everything, the right thing to do is Fourier transform. Okay. Now, it turns out that it's not our old-fashioned Fourier transform of classical computing. There is a version of quantum Fourier transform, yeah, which you can think of as a generalization of Hadamard. Yeah, Hadamard was modulo 2. Quantum Fourier transform is modulo n. Okay. And once you do that, you get either R or a multiple of R. And there are standard tricks which will extract R from this. So all the steps in this algorithm are done. The only thing that was questionable was find the smallest R, and Peter Shor taught us how to do that. So let me just summarize. I'll take questions after the summary. So we started by imagining, or at least abstractly thinking of computation as applying little operations, and the number of operations we need to get to our output from the input should be as low as possible because we want to be efficient. And that is how we modeled computation. We then saw the Mach-Zehnder experiment. I, of course, took liberties with physics in order to explain it in the way I understand it and the way it is useful to our setting. And the important thing that we learned there was that there was destructive interference. So I would like to make a sort of philosophical remark here that all computation, yeah, is trying to move the state into a desirable, configuration. Yeah. And when you are dealing in probabilities, you would like most of the probability mass to go to a desirable state. Now, how do you guide the probability mass to go towards the desirable state? Well, there are classical randomized operations which, sort of take the probabilities towards this. But quantum has one extra trick up its sleeve. It says, not only do I accumulate probabilities, I have the ability to destroy probabilities by doing destructive interference. Okay. And again, trying to quote something. Michelangelo, the great sculptor, is supposed to have said that when he sees a block of marble, he doesn't think about how to make the sculpture. He thinks about how to remove the unnecessary marble. Okay. So quantum computing uses that inspiration of Michelangelo, that we don't just need to guide good probability towards the good states. If we can somehow choreograph things so that probabilities get destroyed from undesirable states, that also will do. Okay. And in one of our examples where two probes could be substituted by one, we did see that the undesirable state got cancelled with a +1 and a -1. This is the extra power that quantum has. Quantum Fourier transform uses this in a very elaborate way. But for all that, we need to do more mathematics than we have allowed ourselves today. So let me go through the thing. Shor's algorithm exploits quantum destructive interference in the form of quantum Fourier transform. So all this is very nice. The truth is, despite what you hear, despite what you read, we are still very far away from doing quantum computing in any way that will be, practically useful. Certainly, Shor's algorithm is, we are not ready to apply, implement Shor's algorithm on any quantum computer in the foreseeable future. Yeah. But I hope I have told you that this is very different from what we thought computation to be. Yeah. And it is remarkable. It is fundamental and deep. I mean, physicists already find something very deep. And yeah, uh, so it's worth studying, worth learning. And there are other things that might come out of the understanding, our understanding of quantum information from a computational point of view. And we are currently in the era of noisy intermediate scale quantum computing. We don't know how to do good error correction with quantum systems. Quantum systems are generally fragile and prone to noise and other effects. So, yeah, maybe I should stop here. Thank you very much for coming to the webinar and listening to me. I'll be happy to answer your questions.
Thanks,
Dinesh.
Jaikumar. It's amazing, wonderful talk. So as
Thanks
usual.
for your help,
So
Dinesh. Yeah, thank you.
yeah. So there are maybe a couple of quick questions if it's okay.
No, of course, any number of.
Yeah. It's okay, right? So Jaikumar, just to go ahead. So you said we all started with the circuit setup in the
That's right.
circuit model, and then we came to finally to this Shor's algorithm.
That's right.
So in terms of this, in terms of, and you said that the size or the number of operations that we do, that is what you really worry about.
Yeah.
So for Shor's algorithm, what is roughly the size of the circuit? If let's say the number that you want to factor is like little n bits, like as you were telling.
Little and bits, yeah. So I don't fully know. People try to optimize, but definitely something like n cubed or something would.
Something.
The bottleneck, if I remember right, is the quantum Fourier transform.
Okay.
Okay. The rest of them perhaps are. So the quantum Fourier transform takes some effort, and then maybe n squared, n cubed. The thing is, yeah.
Okay. So then maybe let's just go on to the couple of quick questions. So one question is, so there is that you explained how you can compute parity of like XOR of 2 bits using just one probe.
Yes.
So, and you also explained nicely this Mark Zenderson experiment of. So is there any physical way by which you can visualize the computing the parity using this sort of a setup? Because seems to be similar, right? You are doing the Hadamard, and Hadamard is doing this beam splitting.
Yeah, I think at least this Max Zender experiment already exists. Okay. So the question is, there will be some, yeah, the only thing is that sometimes, see here, in my where, yeah, the point is on reading this bit, you try to do something to the second bit. Yeah. That is, if you see a 0, I want A0. If I see a 1, I want an A1. That is two different things. Now, Max Zender experiment is described using photons. Yeah.
Correct.
And photons kind of are very shy of each other. To make them interact and get them entangled requires serious experimental physics. Okay. So I don't know whether the photon model of quantum computing is the best to illustrate this, but there are other things, superconducting qubits, etc., where an experiment like this can be easily performed. Of course, you have simulators now of IBM Qiskit, etc., and some of them allow you to even send your circuit into an actual quantum device and read out the answer. All of them will easily do this. Yeah.
Okay. Right. So. Yeah. So another question. So I'm just going through the questions quickly. So another question that was being asked, probably again inspired by your physical interpretation. So is Hadamard gate something which is something that we say theoretical, or is there actually a physical device or physical object?
It's Hadamard gate can be realized in physics. Yeah.
Physics.
So it corresponds to, physicists usually think about it. So let me do this. So if you take the pi by 8, like 22.5 degrees line here, and reflect every vector about it. Yeah. So what would happen to the x-axis? It will go here. And what would happen to the y-axis? It will come here. So it's a reflection about an axis in this state space. Okay. And such reflections can be implemented by corresponding devices in the lab, where, of course, which state is to be called 0 and which state is to be called 1 will have to be negotiated with the experimental setup. Yeah. Here I said, if the photon is going through the up route, it is 0. The photon is going through the bottom route, it is 1. They might say if the photon is horizontally polarized, then it is 0. When it is vertically polarized, it is 1. Or depending on if the photon is in this energy level, then it is 0. If it is at that energy, photon or the device or whatever the physical concept, yeah, if it is in this energy level, it is 0. That energy level is 1. We have freedom to call something 0 and something 1, provided they are distinguishable. Okay. We could call anything 0, anything 1, but then you should be able to set up something which is an equal superposition of 0 and 1, and the other equal superposition of 0 and 1 with a negative sign. And such operations exist in the lab. Single photon quantum computing has reached, it's fully functional. But with single one register, we cannot do too much.
Too much, right. So Jaikumar, again, another question. If you think about so what we have seen so far, I mean, like you've just taken something which was probabilistic and you've added two components to it, and then you try to do some calculations using this. So overall, it looks like everything you don't have anything quantum that is happening. I mean, what where is the quantumness coming in all of this? You've just, after all, you're not dealing with any. It's all probabilities. You're squaring things.
Yes.
So why?
Yeah. Okay. So the thing is, I did this computation in front of you, and people might dispute this, but I'm a classical person. Yeah. And I did it in front of you, and I did this computation in front of you. Then what is so quantum about it? I mean, if I stretch your point to the extreme, yeah. After all, it is doing these computations. The point is not doing these computations with the numbers ourselves. Yeah. The point is that the moment you send a signal, all this computation is happening inside the characteristics of the device itself, the cancellations, etc. And then the result is coming to us. Okay. So if the good question to ask is what is quantum about it? If I do probability with positive numbers, I add, multiply, use stochastic matrices, that is probability. If I do the same probability with the same sort of operations with amplitudes instead of probabilities, use unitary matrices instead of stochastic matrices, allow cancellation, add numbers, and have faith that when a plus meets a minus, it becomes 0. Okay. Then the result is quantum. Okay. Now, this mathematics is actually reflected in the way the statistics emerge out of a physical experiment. And that is the power of mathematics in physics, you might say, that you do a few experiments, extract laws, then you do your paper and pencil analysis using those laws, and then set up the experiment again, and somehow that experiment faithfully does what your calculations show. And if it doesn't, then there is place for new physics. Okay.
Yeah. So Jaikumar, maybe one last question, if it's okay. I think we're almost out of time. But so for instance, so you have all these nice things that we have about quantum computation that you can do with quantum gates. So how do you actually end up implementing these things? I mean, is it like
yeah, so at the moment, I don't think we are at a stage where we can say that this is what quantum computers will look in the future. I mean, my own view. There are other views. People are more hopeful than me. But if we are to think that whether quantum computers today are in the stage where classical computers were in the 1940s when they were being built out of valves and wires and magnets, I think most experts would say we are not there. We are not even where classical computing or was in the 1940s. I mean, remember 1940s, we had a very ridiculous computer. Okay, to add numbers, we needed a computer which was one room large. Okay, and today our mobile phone does more than that. Okay, but we are nowhere near that in quantum. Yeah, but revolutions can happen and things can change. But we are not there. Yeah. And I'm also not very, aware of the latest technology and all that. But
Sure.
thanks.
Yeah.
So,
I think that's all from, I think that's
thanks.
more or less covers all the
Thank you,
questions.
Dinesh,
So
and
thanks.
thank you, everybody.
Thanks,
For
everyone.
Thank
being
you.
here. And,
Yeah. Thanks very much.
thanks, Sushila. Thanks.
Thank you, Jay and Dinesh. Today you took us back to the basics, understanding classical computing through circuits, the Max Zender experiment and spookiness, and helped us, even lay people really understand the foundational components of quantum computing. These are all words that we keep hearing about: superposition, qubits, Hadamard and CNOT gates, orthogonal states. You really made them simple for anybody to understand what quantum computing basically is all about. So thank you for all of that.
I must say
We
one
heard,
thing I did not,
yeah,
which I
sure,
advertised was I would tell you about entanglement, and I
yes.
did not. But maybe somebody else will. Yeah. Okay.
Yeah, sure. Or we will just have another session with you to cover what you could not cover this time.
Yeah.
We heard about Pingala, Euclid, Peter Shor, and how their algorithms are fundamental to computing, and their relevance in classical as well as quantum computing. Jaikumar ended by kind of saying that quantum computing is really not mature yet, certainly not mature. There is still a lot of noise, and it's at best sort of at an intermediate stage. Um, Obviously, it's exciting times because there's so much that's happened, and there are a lot of questions, a lot of open questions, a lot of open issues that we need to deal with. Thankfully, there are still problems that are over 2000 years old, like the factoring problem. Um, in our super connected online world, the fact that these problems are still open is what is keeping us secure, because our encryption algorithms really are unable to break through some of those. So the question is, if quantum computing does mature, then what does that mean for us? Will it disrupt the way we look at basic things like security, information security, and a lot of other things? How communications happen, and a whole bunch of things. Are they going to get disrupted? And if so, what is the shape of things to come? So these are all questions that arise, and we will hold them for the next time we have an interaction with you and others. But thank you very much. This has been an extremely valuable and interesting session. And our audience, thank you also for being here and interacting, asking your questions. Dinesh, thank you. It was important that we had you as the interlocutor for this discussion,
Thank you.
and because you are working in this space, and that's important for us. So thank you again, Jay. We'll see you another time, and goodbye.
Thank you, everybody. Bye.
Thank you. Bye.
Thanks.